Is Jessica Page. I am a PhD student at the University of Alabama Huntsville, and I'm going to talk about the groundwork laid out for estimating TDI arm length variables during the science analysis. So LISA will be 3 identical and separate spacecraft separated by about 1 million kilometers. Gravitational waves will be measured using the phase differences between incoming and outgoing beams. So we're going to have 2 phase measurements, 2 test masses, 2 optical benches per spacecraft. And the spacecraft configuration will be rotating in its orbit, and the laser beams will be propagating in both a clockwise and counterclockwise direction. So for a given distance, or in other words, light travel time between 2 spacecraft, you're actually going to have 2 separate distances depending on which direction they are going in. I mention this because it will be important later. So to measure gravitational waves, the signal must be observable above the noise. Namely, in this work, we are going to talk about the laser frequency noise. So the laser frequency noise are fluctuations of the laser frequency about some nominal frequency, and these fluctuations are not necessarily canceled when you combine measurements, because you are going to have because of the light travel time that it takes to get from one spacecraft to another. So the 2 measurements that I have used in this work are just the standard science, the SIJ and reference tau IJ measurements. So just as an example, if we are only assuming laser phase noise in the data, the science measurement S31 at spacecraft is going to be the measurement at spacecraft 1 coming from spacecraft 3. And it's going to have the phase noise at spacecraft 1 delayed by the, at spacecraft 3 delayed by the light travel time that it takes to get to the receiving spacecraft. So when you combine different measurements, you are not going to cancel out the laser phase noise, because the arms are not necessarily going to be equal. You're going to have 6 different arm length measurements, and so you're going to end up with this noise. The laser frequency noise is by far the loudest source of noise at about 6 or 7 orders of magnitude greater strain than the gravitational wave signals and the secondary noises, as you can see in this bottom plot. The red is the laser frequency noise. So there is a well-established method of suppressing this laser frequency noise, and that is time delay interferometry. So what it does is it combines data streams in such a way that cancels the laser frequency noise, and it does this by delaying some of the data streams, so that if you were to write all of these S and tau terms out with the phase noise components, some of them get delayed and it ends up canceling out. So if laser phase noise is the only noise in the data, you should end up with x equals 0. So x corresponds to one of the channels, spacecraft 1, and this diagram kind of shows what TDI is doing. It essentially has the data bounce off of both spacecraft in both directions, and you end up with no phase noise in the end. But to do this, as you can imagine, you need the delay times to be accurate. So when we delay them, that's an external delay outside of the delays that are already in the science and reference measurements. So these external delays that we do are any of these numbers that you see succeeding a comma. So these numbers need to be accurate to what the actual delays in the data are. and it needs to be accurate down to about 100 nanoseconds in order to suppress the laser frequency noise below the secondary noises. As an extension to TDI, there's also time delay interferometric ranging. So this was first written by Tinto et al. 2005, and it is a method to estimate the delay times that you need to put in the TDI combination from the raw data itself, rather than obtaining the delay times from the onboard ranging system. So this has its advantages. It validates the onboard ranging performance, but also allows you to have to do your gravitational wave inferences on the raw, unaltered phase meter measurements. So this work is an extension of TDIR in that we are going to be estimating the delay times needed for the TDI equations, and the eventual goal of this is to include this estimation as part of the overall LISA data model, so that when you are measuring gravitational waves, you can produce gravitational wave inferences that are marginalized over the uncertainty that you get in the spacecraft separations. So this is what this work is doing. We want to obtain a distribution of the estimated arm lengths, and then you can feed that into gravitational wave measurements. So this also allows you to measure the spacecraft separations in real time, which can allow you to independently reconstruct the spacecraft orbit. So there's another validation. And also the flight travel time / separation / arm lengths, they're all interchangeable terms. Also have a role in some of the other noise sources, like the acceleration noise. So if you want to really understand those in great detail, having data estimated arm lengths and their respective uncertainties could help in that. So this work that I'm talking about here lays the groundwork for these goals by demonstrating a Monte Carlo Markov chain estimated TDI parameter estimation in the rigidly rotating spacecraft configuration, so TDI 1.5, if you're familiar with that. And so this is laying the groundwork. So we're not going to worry about gravitational wave signals or including secondary noises in the simulated data just yet. So yes, this method is using a Monte Carlo Markov chain, an MCMC. So you all might be familiar with this as well, but just as a quick recap, it is a Bayesian way of estimating the parameters by calculating the ratio of posteriors at a given iteration against its previous iteration only. And so you propose many samples and they get accepted or rejected based off of their posterior probability and its comparison to its last previous. So you end up with a large data sample that represents the distribution of the parameters in question. So for this case, the model is the TDI equation, that's TDI 1.5, rigidly rotating, and the parameters are any of the external delays that we need to input into TDI to cancel the laser frequency noise. So anything that is succeeding a comma. And then I write down the likelihood function down here. You can't see it's everything's done in log, so that's the log likelihood. And this is, I'm writing this down here because I'm highlighting the covariance matrix that goes into this. So this is the other noises that we're comparing the laser frequency, TDI canceled laser frequency noise to. So in this case, our data is going to be the X, Y, and Z channels that have the laser frequency noise in it, and the noise that we're comparing it to is the secondary noises. And I have 3 cases of the covariance matrix that we're going to look at. So there is the orthogonal noise covariance matrix configuration, or AET, which is convenient because the way it is formulated, you end up with only diagonal terms. So this should compute faster. But the AET matrix assumes that all of the arms are equal when forming up this noise matrix. And since this study is looking at the arm length parameters, we thought it might be interesting to include the arm lengths in the noise covariance matrix itself. So we're also going to look at the XYZ versions of the noise covariance matrix. So we can still assume that they're all equal and just update that equal arm each iteration by just taking the average. When you do that, you end up with the same element for all of the diagonal elements, and then all of the off-diagonal elements are equal. So that simplifies things as well. And then there's also just the full-blown unequal arm XYZ. When this is also not as bad, because when you write all this out, you end up with a Hermitian matrix. And this one also gets updated every time, and every proposed arm length parameter gets updated in the noise covariance matrix. In formulating this matrix, I assumed that all 6 phase meter and all 6 optical path noises were independent and at the same amplitude. So you could recalculate this matrix using more complicated assumptions, but for now that's what we have, and here is the resulting plot. So it turns out that the unequal arm curve for both the diagonal elements and the off-diagonal elements are basically equal to the equal arm case. So we might expect that the posterior distributions won't be all that different either. But you will notice that the amplitude is much lower at the lower frequencies than the AE and T channels. But I'm actually not going to go into AE and T for now. And first I'm going to talk about the data simulation. So this is the data that went into the analysis. So basically just had to simulate all of the science and reference measurements, and then go from there, feed that into the MCMC, and estimate the external delays. I mentioned that we were doing rigid rotation at 1 day of data, sampled at 1 Hertz. And the arm length parameters that were input into the data were realistic. They were computed from solar system barycenter spacecraft coordinates from a LISA orbit model. And so you end up with arm lengths as a function of time in orbit. So I just took the first day and input those into the science and reference measurements. But since you get a time-dependent spacecraft separations, once you estimate the posteriors, you could do the reverse and estimate spacecraft ephemeris. The secondary noises are left out of the data. They're just included in the noise covariance matrix at their respective amplitudes, but work is in progress to include them and to measure the effects as well. So here are the results for the equal arm XYZ. So the x-axis is the posterior distribution, the samples measured minus the actual measurement that went into the simulation. So I mentioned earlier that we need accuracy down to 100 nanoseconds. So you can see here that we are meeting that. A lot of the medians are at a difference of 10 to the minus 9, 10 to the minus 10. So we are doing well there, and the 1 sigma uncertainties are also meeting that criteria. And as you might expect, the unequal-arm noise covariance matrix case is performing similarly. Yeah, it's doing fine, and it is doing just about the same as the equal-arm. And this was, as you might expect, from the basically the same noise curve that you get using the assumptions that I used, but you could always go in and put secondary noises into the data and measure effects. So there's a comparison. Sometimes the unequal-arm case does better, but sometimes it does worse. So for these assumptions, it's really not going to make that great of a difference. I still need to include the orthogonal channel case in here. But for now, just looking at some point estimates from the distributions, you take the medians of all of the parameters and input them into the TDI equation. This is the residual laser frequency noise. So if you remember from the beginning, you know, it was like 6 or 7 orders of magnitude greater than the secondary noises, and now it is sufficiently canceled. Also, the 90% credible interval parameter for the log likelihood. So I use the 90% log likelihood, and then its corresponding parameters in the distributions. You put that into the TDI equation, and you end up with this. So even out to 90% in log likelihood, we are still canceling just fine. So this is basically the groundwork for the overall goal of including arm length parameter estimation as part of the LISA data model. So the next steps is to also compare this to the AET noise covariance matrix that is in the works, and that will be interesting to see. We want to explore the reconstruction of the spacecraft orbits. This might be a better thing to do once second generation TDI is included, so the time dependence of the arm lengths. But I do plan on doing like a prototype demonstration of reconstructing the orbits, just stepping through different steps in time with their different arm lengths and reconstructing them that way. I think it would be interesting to test on other laser frequency noise simulations. And then I'm also currently working on including secondary noise levels in the simulated data to measure how that changes the cancellation of laser frequency noise and to what effect this process has on the secondary noises. And then the ultimate goal is to include this analysis alongside of measuring gravitational wave signals. We do plan on implementing this into a compact binary analysis algorithm, GBM-CMC, and this will be important because the arm lengths are included in the waveforms. So this is what we mean by making the inferences marginalized over the arm length uncertainties. So, and yeah, eventually do second generation TDI, so account for the time dependence of the arm lengths. So that is what I have for today. Thank you so much for your attention. I am happy to answer questions or have discussions. And yeah, that's it. Thanks.